it's very interesting experience. Although I haven't done anything so far. So this talk is, oh yeah, so before I forget it, this is joint work with one of my former students, Takumi Enomoto. This is his master thesis project, and after that, so now he's working for one of the biggest banks in Japan. Probably his salary is better than mine. Right, so this is a half operator algebra, half representation theory. And one of the most fundamental tasks in a representation theory is that for a given group, so you want to classify all the irreducible representation up to equivalence. And we operate algebras know sometimes it's possible, sometimes it's not possible. The reason is that, well, since the representation theory of a locally compact group is same as the representation theory of a group sister algebra, so let me talk about sister algebra first. Right, so let there be a separable sister. And the S of A is the set of states. Then the set of irreducible representations up to equivalence is the same as basically the unitary orbit of the pure states. Okay. The extreme points of the states are pure states. So it's well known that there is a character one-to-one correspondence between the set of irreducible representation modulo equivalence and the set of pure states. I mean the unitary orbit of pure states. So this is the abstract parameter space of irreducible representation up to equivalence. And but it's well known under the name of Masaki-Izumi dichotomy is that so Borel structure of this space is not necessarily good. And actually, more precisely, when this Borel structure, the canonical quotient Borel structure, so S of A is a topological space with that topology, so it has a Borel structure. The quotient also has a Borel structure, and this is countably separated if and only if A has no typal representation. It means that once you got a non-typal representation, then there's no hope to classify irreducible representations. So this is the classical result. But here we change the problem a little bit to make it easy. So instead of thinking of states, so we consider trace states. Okay? And by definition, the unitary group act on the tracer state trivially. And it turns out that this space is always nice. It is always a standard Borel space. It means that this is classified in a set of circular sense. Although for given sister algebra, then to write down all the extreme traces is a different story. But in set of circular sense, it's classified. So this means that in representation theory, this means that finite factor representations of A are classified for given sister algebra or for given local compact memory. So, right, so when A comes from a local compact group, okay, then tracer states of A correspond to what I call character. Okay. So this is the definition of character. So here, I want to consider a more general class of groups. So G is not necessarily local compact. So G is just a topological. So quite often it is not locally compact in my talk. Anyway, so a character of a topological group G is a continuous function of the group. Okay, satisfying the following three properties. The first one is chi is positive definite in the usual sense. Okay? It is positive definite, and the second condition is that chi is central, so it is a class function. Okay? Chi is a class function. And the last condition is just normalization. So the evaluation at neutral element is 1. So this is a definition, our definition of the characters of group. And of course, this is well, from the definition, you can easily see that this space. Okay, I use this this symbol for the set of characters. Okay. Then, from the definition, you can easily tell that this is a convex space, convex set. So you can talk about extreme point, and we say that we call the extreme point of this space indecomposable. Okay. So now we are out of the locally compact group, but still we have the following correspondence. So this set, the set of indecomposable characters, is in one-to-one correspondence with quasi-equivalence classes of finite factor representations. This is still true, even if G is not necessarily a locally compact. Right, and so here is a trivial example from our point of view. So when G is compact, okay, then every indecomposable character is a normalized character of a irreducible representation. So in this case, when G is compact, then the classification of this indecomposable characters is same as the classification of irreducible representation. Right, but we want to consider much more complicated groups. Right, let me give you a brief history about this subject. I think the first example, the first work in this direction was done by Thomas. So he considered, actually he completely classified the set of indecomposable characters for the infinite permutation group. So it is an inductive limit of finite permutation groups. And he came up with a nice formula, very nice formula, now called Thoma characters with infinitely many parameters. And this work inspired a lot of works, mainly in the Russian school, Versik, Karov, and Russian school. And so it created one field now called asymptotic representation theory. Right, this is the first work. But this is still locally compact. And the next work was done by Bakurescu, and this is really beyond the locally compact case. So he considered the inductive limit of UN. UN is a usual unitary group. Then he considered the inductive limit of U infinity. Again, he came up with a nice formula I'll show you in the next slide with infinitely many parameters. And there are more other results, but probably I should mention this very careful result. So, so there are very nice concrete formulas for these characters, and they contain infinitely many parameters. But when they discovered the formula, they didn't really tell the meaning of these parameters. After then, Carroll came up with so-called method, ergodic method. So this is a method to approximate the indecomposable character of inductive limit group by characters of groups in the finite stage. And with this method, so they gave a very intuitive interpretation of parameters appearing in these characters. Actually, so our main result also uses this method, ergodic method. Right. So, and yeah, I should also mention for you the result. So he considered different kind of investment means, namely the dense subgroup of the unitary group of CL algebra. I'll tell you about this in detail, because this is the starting point of our research. There are many other reasons in this direction. So I'll show you the Berkeley's characters because it is really beautiful. So he considers the inductive limit, and where the embedding map is this map. Then he showed that the character defined this formula is indecomposable. So it contains infinitely many parameters. And you will see this part in a different character for different groups. So this is a typical part, which is very common in this business. And this is very specific about this group. And actually, so let's just show this formula, and this is indecomposable, but he cannot show this family exhausts all the possible indecomposable characters. Later, Kerov and also Boyer observed that the completeness of this family by using the Edred classical result in complex analysis. It's a rather deep result. It's all result in complex analysis. So this family is complete. So this family includes all possible indecomposable characters. Right. This is the very first result in the inductive limit of compact groups. Now, in 1993, I think, and so Boyer considered the following. It's a different, inductive limit of the unitary group. And we operate algebras node what this embedding means. So it is an embedding you use for the CL algebra. So the inductive limit group obtained this way is a dense subgroup of the CL and the unitary group of the CL algebra. Right. And the topology is different. Topology is, we consider the topology, inductive limit topology here. So here you have normal topology, but our topology is different. But it doesn't matter in this case. Anyway, so Boyer's result is that, so Boyer showed that, so this list of characters. So basically every character is a product of power of tau. Tau is a unique trace. Product of a power of tau and a power of tau bar, the complex conjugate of tau. And that's all. So, and he used Strater-Boyk-Resk algebra. Actually, so Strater-Boyk-Resk worked on the inductive, general theory of inductive limit of compact groups, and he introduced some AF algebra associated with inductive limit. So, actually, so I had a student a few years ago, and I was looking for a nice problem for him, and easy but interesting problem, and then I told him to read this paper, the proof. So possibly, so we can get a new proof using basic Kerov method. And he said he had a look at the paper, and he told me that he cannot really read the paper. Why not? Well, I had a look at the paper, but then I realized that I can't really read that paper. Probably it's proof handicap. So we decided, we decided to be more ambitious. We try to generalize the situation as much as possible, and then we try to create a new proof. So this is a starting point of this research. Right, so to state our main result, one of our main results, let me introduce notation, AF algebras. So let A be an AF algebra. So it's, by definition, the inductive limit of finite dimensional system algebra. Okay. And sometimes I want to consider non-unitary system algebra. So for the unitary group of a non-unitary system algebra. So what I mean is this. Okay. So it's a set of unitary in the unitization who's different from one belongs to A. So this is the unitary group with non-AF algebra, non-unitary algebra. Right. since A is an inductive limit, so we can consider this inductive limit group. So this is a, well, so since this is an F algebra, n is finite dimensional, so the unitary group of n is a compact group. So this is an inductive limit of compact groups. Okay, and here for this group, so we consider inductive limit topology. Okay. So, and we can, of course, this this group is embedded in the full unitary group. So here the natural topology is a norm topology. But I should mention that well, the inductive limit topology here is usually strictly stronger than the relative topology of this group. Here the topology is a uniform topology, unitary, the norm topology. And in general, the gap between these two groups could be drastic. And this is a typical example. So as an AF algebra, consider the set of compact operators on the separate infinite dimensional Hilbert space. Okay. So this is the inductive limit of full matrix algebra. So for this group, the inductive limit group, we get new infinity of Voigt. And Voigt-Fresco's result says that there are infinitely many, actually continuously many, type 2-1 factor representations, okay, for this. But on the other hand, for the full unitary group, okay, it's norm-closure. Then it's known that actually it's all the Voigt-Fresco result. So Kirov completely classified its irreducible representation. He showed that there are only countably many irreducible representations. So it's type 1 group. It's a huge group, but still it's type 1 group. And basically every irreducible representation is generated by the fundamental representation and the complex conjugate of the fundamental representation by TensorFlow. So the difference between these two groups is could be very, very large.
So it's a group for AF does not depend on the towers of AN.
Yeah, that's a good question. And the answer is it doesn't.
No.
Because Georgi proved, when Georgi classified AF algebra by using the dimension group, he showed that if you have two AF algebras and the two-dimensional groups are isomorphic, then the inductive limit algebra without taking norm closure are isomorphic. That's what Georgi proved. So it means that this other topological group, this doesn't depend on the particular inductive limit decomposition. That's just a direct consequence of Georgi's classification. Right. So to state main result, I need to introduce determinant associated with homomorphism. So we are still working on F algebra. So let's phi be homomorphism from the K0 of A to Z. Okay? We fix one homomorphism. Then for unitary in the finite stage, so we can associate the determinant with respect to phi by using this spectral decomposition. Okay? So by this formula, then we can introduce a determinant. And when A is just an n by n matrix algebra, then its K0 is Z. So phi, assume phi is just an identity. So this is Z when A is n by n matrix algebra. Then in that case, then this is a usual definition of a determinant. And it turned out that this formula does actually. So this determinant is a well-defined map, continuous map from the inductive limit group to the torus. And it's a homomorphism. So this has a one-dimensional representation. This group has a one-dimensional continuous representation if this is not empty. But this determinant doesn't extend to the norm closure. You can show that it doesn't extend to the norm closure. Right. so here is one of the main theorems. So A is infinite dimensional unital simple F algebra. So it includes, this class includes the CL algebra. Then first we have the following list for the inductive limit group. So every indecomposable character is a product of three things. The first term is a product of extreme traces. Next one is a product of complex conjugate of extreme traces. And the last one is data. Okay. So character defined this way is always indecomposable, and they exhaust all the possible indecomposable characters. And for the full unitary group, it's not very different, but we don't really have a determinant term. This is the result for the full unitary group. So this way, so we get a new proof of Boyer result in the case of CL algebra. So this is a complete classification. And the proof uses a Bell's-Calc algorithmic method. So I'll tell something about it at the end of this talk. Right. So once you get the result for F algebra, then there is some trick to extend the class of C-star algebra. And then we get the following. Oh, it's an easy trick. So let there be a separable infinite dimensional unital simple exact C-star algebra with treasure topological answer. Forget about this definition. Let's think of say irrational rotation algebra. Okay. Thanks to Elliott Evans, it is so irrational rotation algebra is in this class. Of course, F algebras are in this class. Then, so this time, so the unitary group is not necessarily connected. So first we consider this the connected component of the identity. Then it turns out that the result is the same as F case. Okay. For the connected component, then we have this list. All the characters, all the indecomposable characters come from extreme traces, product of extreme traces, and product of complex conjugate of extreme traces. But okay, algebra A in this class might have a non-trivial K1. So for the full unitary group, we have an extra term actually coming from the character of K1. So this is the complete classification. And actually, the proof uses the fact that in this class, then you can embed F algebra preserving K0 in this case. And by using that embedding and using the classification result in the case of F algebra, then so you can get this statement from the previous result. Right. So, and actually, maybe you already realized that. Well, in this, well, there is a bit different situation from the classical representation theory. So, if you have two representations, irreducible representation, then you take tensor product. Then usually the tensor product is not necessarily irreducible. So the tensor product is decomposing into irreducible pieces. But in this game, so in the case of finite factor, 2-1 factor representation, the tensor product of two 1 factor representation is again 2-1 factor representation. That's why you take product of two indecomposable characters, then you get again indecomposable characters. So in other words, so in this business, this space has a structure of semigroup. It is closed under product. And well, in the case of irrational rotational algebra, then so this theorem says that as a semigroup, so this space is isomorphic to this. So this part comes from the character of K1, and this part comes from the power of tau and power of tau bar. How is the normalized trace? Right. We also have a result for a factor. Actually, it's a consequence. Well, in the case of a hyperfinite, then it is just a consequence of the result in CL algebra. So let R be a 2 factor, not necessarily hyperfinite. Okay. And we consider the unitary group, but now the topology is strong operator topology. Then we have the following complete list. Again, the result is the same. Actually, so it's the situation is very similar to the cyst algebra case. So first, we prove this for the hyperfinite 2-1 by using the result in the CL case. Then there is some trick to deduce the general result from the result of the hyperfinite 2-1. Because, well, so you can embed a hyperfinite 2-1 factor in every 2-1 factor, and using that embedding, then so the main ingredient of the proof is, as I told you, the Bell-shaped curve algorithm method. But other than that, we need an analog of sure value duality. We also need that for the proof of the AF case. So let me mention. So H is Hilbert space, and H bar is the complex conjugate of H. So H bar is also a Hilbert space with this operation. Then for fundamental algebra in B of H, so we can consider its complex conjugate, okay, in the B of H. Now we have the following analog of sure value duality. So M is here I should emphasize that this is infinite dimensional, because if M is a finite dimensional, then this is not true. If M is an infinite dimensional factor, then we have the following analog of sure value duality. Namely, so we are doing is that we're considering the product of P copies of fundamental representation and Q copies of complex conjugate of fundamental representation. Then we are seeing what this fundamental algebra generated by them. The answer is just a tensor product of the fixed point algebra and the permutation group SP and permutation group SQ. So if you don't have M bar part, it's just an analogy of sure value duality. But when you have both M and M bar, then actually this is true only for infinite dimensional factor, because let's think of the case where P is 1 and Q is 1. Okay, let's think of the case where P is 1 and Q is 1. Then this is a tensor product of the fundamental representation and its complex conjugate. So in the case of finite dimensional H, then so U tensor U bar always contain the identity representation. So U tensor U bar is never be a factor representation, but for infinite dimensional case, it is always a factor representation. Actually, and U tensor U bar generates the whole M and M tensor M bar. And actually, the proof of the theorem in the case of F uses this theorem for the hyperfinite 2-1. So for the proof, we have to prove this for the hyperfinite 2-1 first. And that can be done by using a finite dimensional approximation. Then once you get this result for the hyperfinite 2-1, then there is some trick to get a result for the general case. So by the way, so this when M is a B of A, so type 1 factor, then this result was obtained by Akiba in 73. So this is a generalization of the Kyoto result, if you like. Anyway, so we need to show this first to prove our main result in the AF case. But that's a finite dimensional approximation. Now, I'll talk about a non-unital case because, well, so in this talk, I started with Voigt-Lescud's result, and so his group, U infinity, is an inductive unit group associated with a compact operator. So the F algebra is non-unital, so we also need to work on non-unitary F algebras. So let F be a stable simple F algebra. Then, in this case, we don't have threshold states because it's stable. We don't have threshold states. So instead of considering threshold states, we consider threshold weight, the set of lower semi-continuous semi-finite traces. Okay, we consider this threshold cone. And they have common domain so-called Petersen ideal. So you can add two traces, although they are infinite traces. Right. Then it turns out that, okay, if U is a unitary in the finite stage, then U minus 1 belongs to the Petersen ideal. So this makes sense. It's a finite number. And actually, so this map is continuous for every threshold. So this function makes sense. So for two threshold weights, we define this function. And remember, this type of formula appears already in the Voigt-Lescud character. Right. And it turns out that actually this function is positive different. The reason is that it's easy to show that this function is conditionally positive different. Well, you can show it from the definition. It's easy to show that. And well, thanks to classical Schoenberg theorem, this exponentiation is then positive different. So this way we can get a character of the inductive limit group, not the whole unitary group though. Right. Then the next main theorem is the following. So if A is a stable F algebra, stable simple F algebra, but not isomorphic to the compact operators. And it's very unfortunate, but we need this assumption. So the threshold point is finite dimension. For the moment, we need to assume this. But I believe this is just a technical condition. If you work hard, then you can get rid of this condition. But for the moment, I can. Anyway, the result is the following. So we have this complete list. So every character, every indecomposable character is this product of this exponential character and the determinant. Right. So the situation is completely different from the unitary case. But we still have this complete list. And let me talk about the fundamental algebra case, fundamental algebra analogy. So now the analogy is a two infinity factor. So M is a two infinity factor. It has an infinite trace up to unique up to scalar multiple. Right. Then we cannot really think of the whole unitary group, so we consider so-called LP group. So P is the number rather than 1 equal to 1. Okay. Then we consider the following subgroup of the unitary group. The set of U whose difference from identity has a finite LP domain. So this is a nice Polish group with invariant method, by invariant method. So for two number A and B, and if U belongs to the L1, then again this exponential character makes sense. But when P is not 1, then this doesn't make sense. But still, when P is 2, then this formula makes sense. And it turns out that this coincides with chi AA when U belongs to the L1 group. Then we have the following classification. Okay, when P is 1, then this family exhausts all the possible. First of all, so this is always indecomposable character. And this family exhausts all the possible indecomposable characters. And for when P is larger than 1 and less than or equal to 2, then so this family reduced to this family, the other family here. But still we have a complete classification. And when P is larger than 2, then there is no non-trivial character. Right. So this is the complete classification. And well, let me mention some question problem. So in view of our main result, it's very tempting to conjecture this. So assume A is a unital separable simple system. Then it's clear that this product, okay, our prime are extreme traces, and psi is a continuous homomorphism, so one-dimensional representations. And it's clear that this product is an indecomposable character. The question is whether this family, okay, exhausts all the indecomposable characters. So this is the problem. Does the above set exhaust all the indecomposable characters? And well, the first test case, of course, is Janssen algebra. So far we get this for F algebra, or more generally, tertiary F algebra with torsion-free K. This is true for torsion-free in that class. Beyond that class, it's off. And second problem is that compute this space for more general F algebras. So in other words, non-simple F algebra. There are some very natural non-simple F algebras like gauge invariant C algebra. So it must be an interesting problem to classify this space for the gauge invariant C R. But the result should be very complicated because so gauge invariant C R has a quotient isomorphic to the unitization of compact operators. So the result should be very complicated in this case. And the last problem is that you start with 2 factor, then then you can make a 2 infinity factor LP group. Then so when P is between 1 and 2, including 1 and 2, then this group has a character, so 2-1 representation. So you can ask the relationship between the original 2 factor and the resulting 2 factor. When R is hyperfinite, then the resulting 2 factor is always hyperfinite, but for other 2 factors, then I don't know. So I have probably 8 minutes.
Yeah.
So probably I should say something about the proof. So that's the main ingredient is the Bell-Ship-Kerr algorithmic method. So this is a way to tell the indecomposable character from a sequence of characters in finite state. So assume Z is an inductive limit group. Okay. And typically, these groups in the finite stage are compact. But we also apply this method to the case where Gn is a unitary group of the 2 factor. So the precise condition we need is the following. For Gn, so this set, okay, this set is countable. We need that condition and the unique decomposition. We need unique decomposition. So typically, Gn is compact. But the unitary group of 2 factor also satisfies this assumption. So in such a situation, then so basic curve says the following. So for any indecomposable character in the limit group chi, there exists a sequence of indecomposable characters in the finite stage, such that So chi n combines to chi uniformly on every group in the finite state. And you can choose this sequence such that restriction of chi n plus 1 to the n contains chi n. So this is a very powerful method, and also, but well, it's kind of philosophy, and you cannot really apply this method alone. Apply this method to a concrete example without doing anything. So to apply this method, then you have to do some estimate in general. So it's a kind of philosophy, but it's really a nice idea. So in our case, so let's talk about well, AF case, unitary AF case, simple unitary AF case. So in our case, finite dimensional, the groups in the finite stage is a compact group. Actually, direct sum or direct product of unitary groups. So let's talk about unitary group instead of I use instead of UN, I use D for the size of the group. So this is let's recall the representation theory of UD. And it is known that the set of irreducible representations is identified with set of signatures, so-called signatures. So a signature of length D is a tuple of integer, decreasing tuple of integer with length D. Okay. And it's well known that there's a one-to-one correspondence between the irreducible representation UD and the set of signatures of length D. And in general, signature has a positive part and negative part. Okay. This is just a tuple of integers, decreasing tuple of integers. So it has positive part and negative part. So you can divide the signature in positive part and negative part. Then you can regard this as a Young diagram. Okay. You have decreasing tuple of positive integers. So you consider, so you can regard this as a Young diagram. So in other words, so every signature is characterized by two Young diagrams and the size of the group. Okay. So this is enough information for us. So you have two Young diagrams and the size of the group. So let's use this notation for the corresponding normalized character. Okay. We have two Young diagrams. Young diagram for positive part and the Young diagram for negative part, and this is the size of the group. And when the negative part, the negative Young diagram is empty, then this is nothing but a normalized Schur function. Okay. This is a classical Schur polynomial. So this is a representation theory of the unitary. Then the estimate we use is the following. So this is a kind of very strange estimate. But it's true. What we do is the following. So we fix two Young diagrams. First, we fix two Young diagrams. Then we let the D size of group goes to infinity. Let D go to infinity. Then we have such an estimate. So there is a constant depending on only the pair of Young diagrams. It doesn't depend on the size of the group. And we have this. In other words, if you fix two Young diagrams, then when D is large, then this normalized character behaves like a product of power of trace and a product and power of complex conjugate of trace. So actually, so the statement in our main results says that well, every indecomposable character is a product of traces and complex conjugate, and this is the way we get the traces from the character. Right. So this is good. So in our particular case, so we are working on AF algebra. So in AF algebra, so each AN is just a direct sum of finite dimensional system algebras, matrix algebras. So our group in the finite stage is just a product Now we apply. We want to apply the velocity curve algorithm method and we want to use this estimate. Then for that, then we need to bound the size of Young diagrams, because this is true only, once you fix Young diagram, then you let D go to infinity. So we need a way to bound the size of Young diagram appearing in the character of these groups. And for that, we use a nice observation, very easy but a nice observation of Konkov and Olszewski. So in our case, so we are thinking of an inductive limit for F algebra. So we can assume the first group is just a complex U1. So the first algebra is just a complex number. So it's first group. Then we apply velocity curve methods. We have a sequence of characters. Then we restrict chi-n to the first group. This is the character we get. Okay, restriction of the character chi-n to U. Then we use a free expansion, since this is a positive definite. So these coefficients are non-negative. So this way, we get a sequence of probability measures on Z, okay, converging sequence of probability measures. Then, so their observation is the following. Assume you have a tight family of probability measures on Z, having force moment. Assume that the second moment diverges. Then this ratio should diverge too. And this is a really easy observation, but it's really nice. And in your situation, then actually, so we can show the following estimate. So this never diverges. It means that the second moment should be bound. And from this information, then I can deduce that all the Young diagrams appearing in the final stage actually have bounded size. And to compute this, concretely compute this second moment series, then, well, I should use this Harris-Chandler Exclusive integral. I don't really show you the concrete form, but the method to compute the second moment is this Harris-Chandler Exclusive integral. So I think my time is over.